Hi, in this video we'll be looking at post-processing the results from Elmer. So I am back to my Arch Linux host, and as you can see I put all of the files we generated with Elmer Solver in the same project directory, and these are the two files we will be looking at. So let's open the log first. We are interested in the 5 eigenvalues, so let's put this window on the side. And I'm gonna open Julia. You could use any other scientific programming language for that, or maybe even just a calculator. But what I want to show you is how to go from the eigenvalue to the resonance frequency. So cool thing of Julia is that it supports Unicode, so /lambda and tab will become lambda, and let's call the eigenvalue lambda, how it is normally done in algebra. So if we want the resonance frequency, all we do is to compute this value, and this is happening because lambda, the eigenvalue, is the square of the angular resonance frequency. So if we want the resonance frequency, we do this. So let's do better and let's calculate all of them. So we're going to create a vector. Alright, so let's do element-wise operation on this vector by adding dots, and we got ourselves all of the resonance frequencies, and we can observe that there are frequencies that are very similar to one another. This goes by the name of degeneracy. So it means there are more than one eigenfunction for the same there are more than one eigenfunction for the same eigenvalue. These are actually slightly different, but there's good chance that they're actually the same for real. So let's see if by looking at the VTU file we can understand something more. So let's open up Paraview. Let's dismiss this first welcome screen, and let's go to open the VTU file. And in case you're wondering why there is 0001, is because on time domain or scanning simulation Elmer will create many VTU files, but we will see that maybe on another video. So we can apply to import all of the entities inside the VTU file, and we can see that among the entities there are also our displacement eigenmodes, and this is our bar. We can use the left mouse button to rotate the view and the middle mouse button to pan around. So let's have a look. Maybe we can color this bar somehow, and yes, we can. So we decided to color the bar on a scale of colors that go from 0 to the highest value of the magnitude of the displacement eigenmode vector. So for each point of our metal bar, the displacement field is actually a 3D vector with x, y, z components, and we are coloring using the magnitude. So we can see right away that the face we fixed is not moving, and that's correct. But you can also see that there is a very large value in here. So how we should interpret this number? Well, it turns out that the modes of vibration actually are related to the vibration of a bar in some kind of realistic condition, for example, maybe driven by a force applied in the air, through a relation that is called modal superposition. So what is normally done with this eigenfunction is to normalize them so that they go from 0 to 1, and then at steady state, if there is a forcing factor, for example, some sine wave force applied over here, the response of the bar will be a sum of all of the eigenmodes, of all of the eigen functions, with certain coefficients that depend on the boundary conditions and the forcing factor. So the value this thing has really is not that important. So let's see whether we can actually have a look at the deformation of the thing, like how the bar will look like when it vibrates. So we can select our data and click on warp by vector. Since we're seeing that the value of displacement magnitude is not that realistic, just let's scale it down to something big enough for us to see, but not huge to make very little sense. So let's do just that. And maybe let's also put a data grid so that we can see the sizes involved. So yep, looks like for this first mode of vibration, the bar is bending pretty much to 45-degree direction with respect to where it was originally. We could superimpose the original one, and maybe, since we are at it, let's make it just so opaque, right? Yeah, I like this. Okay, so we can see the bar at rest in there and the displaced bar, so it's kind of rotated this way. So if we had to drive this metal bar with a force at exactly this first resonance frequency, which was 824 Hz, we will pretty much multiply this shape by a sine wave, so we will see this bent shape pretty much moving around the rest position. So probably there is a way to animate that with ParaView, but for the time being, let's just imagine this solid shape bending around the opaque resting position. So we can have a look at the second mode, which really does look very similar, but it is just that with respect to the resting position, the bar decided to bend around another direction, but in the very same fashion. So it was going like up from this point of view, at least on the first again mode, and on the second it's going down. So this shows us that essentially the first two modes of vibration are pretty much the same thing, and that's why they have the same frequency. It is just that the bar is vibrating on the same pattern, but along two different directions. And the ambiguity is probably given by the fact that there is only one boundary condition, strong boundary condition in there. If we add more boundary conditions, we constrain the number of possible vibrations, and so we will have less modes of vibration available for a single resonance frequency. Let's have a look at the mode 3. Alright, that's pretty cool. It's like bending in the middle. And what about the fourth? Yeah, same kind of thing, but again around a sort of rotated direction, which will explain why also for these two modes the frequencies are the same. So I guess we're gonna see that a lot. So for the last mode, alright, so it looks like this vibrational mode is about the bar vibrating around its own axis. Okay, so let's keep the bar fixed for the moment. I'm just gonna even delete this filter, and let's just clip the bar along the middle so that we can have a look at the displacement field inside. So maybe I should select this. Yeah, there we go. So things look pretty good inside. Nothing surprising going on. Let's go on the second one. Same thing to be said. Let's go on the third. All pretty smooth looking. On the fourth. Not too bad. On the fifth. Yeah, we confirm now that we have sliced the bar in two, that in fact the axis of the bar is not moving at all, but we can also see weird things happening inside, and these probably are not very realistic. And let's go ahead. Let's go back and let's look at the frequency. It is a very high frequency, so probably what is going on over here is that our mesh size is too big to capture the displacement field with accuracy. So we should probably repeat our analysis with a higher mesh value, with a smaller mesh value actually. I mean smaller mesh size. If you want to model the bar at such a high accuracy, at such a high frequency with high accuracy. Okay, so I think this can conclude our video, and I will probably talk about a few more things on my blog, where I write down the episode for this project. But for the time being, all I think is best to be reported through video has been reported, and I guess I will see you guys on the next mini-series about some other numerical analysis project.